Hello? Can you hear me? Yes. Good morning. Welcome to the new edition of Control Systems 2, once again. As usual, we start with some administrative notes. One observation, you have started using, and we're very happy about it, one of the two labs, J44.4. We have noticed that some of the DocuBots were not left in charge after you left. Please do so, otherwise the next batch of people that comes in won't have a DocuBot to play around with. We've noticed that sometimes there are hardware failures of different kinds, batteries that get loose, or maybe, I don't know, bits and pieces that fall off. If that's the case, don't worry, but please do send an email to one of the hardware TAs and tell them what the ID of the bot is. It's typically printed on top of the bot so that they can take care of it and fix it. One other observation is that, of course, please leave the room clean. We found remnants of foods and eating and stuff, and that's always bad practice. And make sure that if you're the last person to leave the lab, windows are closed. That's like an ETH policy. And one other thing is that we upgraded the locks on the doors. Has nothing to do with the course itself. It was a planned upgrade since months. Now there is electronic access. This caused the door to be locked, and we weren't really aware of it. So some of you guys couldn't have access to the lab. We're sorry about it. Should be fine now. The door should be open at all times, so don't really worry about it. But please contact either Claudio or one of the other TAs or myself in case. If you're locked out, we'll be happy to let you in. So today is the competition day. Call it as you wish, the trial day, or maybe something adds less pressure, but you have received an email and the various instructions on Piazza to make sure that your controller actually compiles and works. So make sure you go there today and yes. So make sure you go there today and bring your lucky duckies, and good luck. We've seen that, I'll give you a tiny spoiler, but my assistants told me that they've tried all your stuff, and most of it is great. They had to put particular effort in trying to break down your controllers, so good job. And last thing, feedback. So we're noticing, I guess it's a natural thing, as time passes by, the number of people that provide feedback on the lectures and the exercises, both the hardware ones and not, are reducing. And a normal thing is that the people who provide feedback in general are always those that are at the end of the spectrum, either the very happy ones or the very unhappy ones. So we do actually read the feedback. I read the feedback, and I take action upon it. And sometimes it's difficult to understand what's the feeling of the class if I only get the very bad reviews or the very good reviews. I can't take decisions based on 2 feedbacks, right, out of 300 people. So even if you are not one at the extremes, it's valuable for us and for the course if you just pitch in. Say whatever you want to say. Just provide feedback, okay? So if we have a statistically significant number of people that provide feedback, then it's useful. Any questions before we start? Comments? Doubts about the hardware exercises? No? Okay, so some of you didn't like the fact that we're using the Surface Book. We're writing on stuff instead of using the Blackboard. Some of you love it. It's difficult to understand what the right thing to do is, but I'll continue with this test today. Give us a few more classes. If it really doesn't work out, then I'm happy to go back to the Blackboard. And in general, if you feel that there's something wrong during, like I don't understand something, or there's more value if I take it slowly and do it at the Blackboard, please just raise your hand, and I'll be happy to just go to the Blackboard and do things there. Okay, so Finally, this is called the control system class, and up to now we really didn't talk about how to design controllers for given situations, right? So today we're going to start somewhat the second part of the course, where we will be talking about synthesis as opposed to analysis of feedback systems. That means that up to now, we were worried about how do we check if things are right. And right means how do we check if we're given a plant, or at least a nominal plant, an uncertainty model, a controller. How do we check if the system is stable, if it has performance criteria that are satisfied, and if robustness, that is robust stability and robust performance, are actually satisfied as well. So last class we introduced these, formally I guess, these definitions of nominal stability, nominal performance, robust stability, and robust performance. And we have introduced a way to represent systems, feedback loops, instead of the typical block diagram that I'm sure you all know by heart, and if we were to wake you up in the middle of the night, you might not remember your name, but you will remember how to write down a standard feedback loop. So we introduced this alternative approach, which is called it's based on the linear fractional transformations, and it's a way to highlight some components of the loop that are for some reason relevant. So in the context of a robustness analysis, what we did was isolate the uncertainty models, the delta sets, and we saw that it was convenient to use this representation because we could isolate the nominal part of the system, of the process to be controlled from what we assumed to be the uncertainty on the model. And then through this way, it was easy to see what the effects of uncertainty on the system were. So we wrote down what the transfer functions were in this case, and we saw that we used this formulation to analyze robust stability and robust performance. And we first introduced we didn't introduce, but we recast the small gain theorem, which we saw was a powerful tool to determine sufficient conditions for stability. We saw how that same thing would apply with this new LFT structure. And then we started looking at performance problems with the idea of moving towards robust performance. We first noticed that a nominal performance problem, that is, for example, the conditions you need to have on the various sensitivity functions of the loop in order to, for example, have good disturbance rejection or noise rejection and good tracking, and how to recast that in a robust stability problem. And we used this notation trick, if you want, which was simply to wrap up the noise contribution through a weighting function. We wrapped it back up in the loop, and we saw that the math turned out in the same way, that the same conditions were derived from nominal stability or from the analysis of the nominal performance, or the, let's say, delta approach and the robust stability approach for the nominal performance problem. So we saw that by putting together both this trick of transforming nominal performance into robust stability and the classical robust stability, that is, including the model uncertainty explicitly in the loop, we could then again reuse this linear fractional transformation approach and use the condition from the small gain theorem that we had previously derived to find conditions on robust performance. And so by applying just the small gain theorem, we saw that we got our nice infinity norm condition on the M transfer function. The M transfer function was fundamentally the uncertainty transfer function. But we even observed that this condition was definitely correct, but not really the best we could do. Because when you do norms measure sizes. The sizes take into account magnitudes, but not necessarily other information. For example, the phase or other priors, that is, other known pieces of information, for example, about the structure of the uncertainty set. So we saw, speaking again about uncertainty, that if there is one thing that is sure, is that every time you write down a model of a system, you got it wrong somehow. But it's not clear how to associate physical reasoning on uncertainty. For example, I don't know, we don't know high-frequency behaviors of a system because it was difficult to do system identification at those frequencies. Or maybe we simply neglected to model some dynamical phenomena because maybe they're not of interest or we weren't aware of it. So it's not really clear what is the best uncertainty parameterization in order to capture the phenomena that we have not modeled. On the other side, we saw that there is a big variety of different uncertainty parameterizations that can be used. We focused on the two most, let's say, typical one, which are the multiplicative uncertainty and the additive uncertainty. So we noticed that this approach with the M delta structure, with a linear fractional transformation, did provide us conditions, but these conditions weren't very stringent. They're very conservative. So we introduced this nasty beast called structured singular values, which basically we saw that they are somewhat of an analog of the stability margins that you saw in single input, single output systems when you did control systems 1. And in particular, we compared it to a gain margin. So basically, the structured singular value, which has a very ugly definition, and we saw that sometimes it's even impossible to actually evaluate, if not through iterative numerical means that we're not going to get into, represents what is the smallest possible uncertainty that sends our system unstable. And also, what's the minimal possible gain, if you want, so to speak, that sends your system unstable. So we looked at some E-simple problems, and in particular, at an example based on 2x2 single input, single output system, where we analyzed a disturbance rejection problem. And we compared we reached these graphical representations that somewhat allow us to gain an intuition in what is actually going on. And we saw that there is a very nice comparison to be made. So if you're only studying robust stability, what's going on is that this is an Nyquist diagram. If you have your nice plot of the behavior of the open loop transfer function, when you have, in this case, multiplicative uncertainty, what is going on is that at every point in frequency, this would be omega 1, omega 2, whatever it is, at every omega in your spectrum, there is uncertainty. So this means that there is a family of curves that could represent your actual model, because the whole point of uncertainty is that you don't really know what the real deal is. You know what is your nominal plant, and you know that there is a region where your plant could actually behave. So at every point in frequency, we could represent this with bigger or some uncertainty, represented by these circles. And we derived a condition that showed us that stability is guaranteed, robust stability is guaranteed, when at any point in frequency, these circles don't intersect with the critical point. And on the other side, when we studied the robust performance problem, we saw that the deal was pretty much the same, only that there was uncertainty even on the critical point. So now the condition can be seen as these two uncertainty sets must never intersect. So of course, it's a more stringent condition than just robust stability. And why is that? Because when you introduce perturbations in your system, of course, the performances could go out of the window way before your system goes unstable. But what typically you need in practice is good performance. Of course, if your system goes unstable, you've got a big problem, but you typically even need good performance. So it's important to remember that the robust performance problem has practical applications, although it's kind of tough to analyze in a theoretical way. So, as I said, we are now moving towards the synthesis part of the course. That is, how do we actually synthesize controllers to meet the various performance criteria and objectives of a controller that we previously introduced. So what we're going to do today is take it step by step. So we're going to start looking at how to control a MIMO system. And if you ask your favorite control engineer, or if you pick up a book or go on the internet, you'll see that there is infinite, maybe not, but plenty of ways to approach a control problem, right? So instead of just putting out there what are the most famous ones, the most used ones, we'll try to do it step by step and try to build a logical approach to how to choose a controller and which approaches make sense. So now this is a general approach, a general way to investigate in life and science, especially mathematicians like it very much. When you are facing a problem that you do not know the answer to, well, what if you try to just recast it in a problem that you know the answer to, and then use the tools that you already had developed to solve the problem? So in this specific case, the first question that we're going to ask ourselves is, okay, we need to control a MIMO system. Now, we know that MIMO systems are a little bit more complex than CISO ones because they have these concepts of directionality, these concepts of different channels of inputs and outputs that definitely mess things up. But is it possible to just make the MIMO control problem become a union, a bunch of CISO control problems? Because if that's the case, then we can just use all the tools that we know from control systems 1, and the deal is done, and the problem is easy. So we'll ask ourselves a question, can we make a MIMO control problem become a set of CISO ones? And we'll see that the answer is yes, of course, sometimes. It depends. And it depends in particular on how much these input and output channels of the MIMO system are coupled, or are how much interaction there is between the different channels of a MIMO system. If there is very little interaction, it means that basically one input only affects, or prevalently affects, one output. So we can just go and check the different inputs to see which input best matches a certain output, and just use a CISO control approach. And, but sometimes that is not possible because actually in practice it turns out that MIMO systems are often very coupled. The different inputs and outputs have interactions. But still there is a value in seeing what the approach of decentralized control, it's called, is. And so it all verges on this concept of interactions. So of course the next step is how do I know if the systems if the MIMO system has these interactions? Is it possible not only to have a qualitative understanding, but can we quantify what are the interactions of every single channel? That is, what is the effect in some way of every input on every output of the system? And so today we'll talk about an approach to evaluate these interactions. Not the only one that exists, but definitely the most used. And then we'll see, okay, so if there aren't interactions, if these channels are independent, we can go with the so-called decentralized control. So each channel can be controlled as if it were an independent CISO system. What if instead it's very coupled? Is there something we can do? Well, again, remember your mathematician best friends. We'll first try to ask ourselves the questions, can we just, even if all the channels are very interconnected, can we just figure out a way to detangle the interactions and remake the problem again a CISO one? If that's the case, we can then fall back into the centralized control, which is very easy. If not, then what to do, right? And what to do in that case is going to be the argument of the next lectures. So today we're going to start by talking about decentralized control, and we'll talk especially about how to determine if if we can use decentralized control for a MIMO system or not. And we'll talk about this tool called the relative gain array. So, as I more or less said, let's just put the thoughts in order here. There's two main philosophies when we go about controlling MIMO system. The first one is, let's take the complicated problem and make it an easy one. That is, let's try to avoid the MIMO complexity and recast the MIMO system in a CISO one. That allows us to use so-called decentralized control, which is a way to make so that every input signal just affects one output. But of course, even if that's the case, there is a natural question that arises. Okay, we determined that one input affects majorly only one output. What's the best way to choose which are the best inputs to control each output? It's the so-called pairing problem. How to understand what's the most efficient way to use the structure of the system to do feedback control. And then we'll see that when it's not so straightforward, we can use this decoupling control approach, it's called, to try and see if we can detangle these interactions and make it a simpler problem by adding some sort of pre-filter, a pre-compensator, it's called. And then there's another philosophy instead that says, well, if all these simple, let's say, simplifying approaches failed, well, what are we going to do? Then we're going to implement some fully multivariable controllers, or so-called, let's say, centralized control approach. And we'll see that there are many ways, of course, to do centralized control. In the rest of the course, we'll touch upon two main approaches, which are the families of the linear quadratic regulators and H-infinity control. And we'll touch upon maybe other approaches as well. So a couple of observations I would like to make before continuing. When you typically move to formalize fully multivariable controls, things become messy. So typically, you do not say we're going to design a controller, as you did in single input, single output systems. Instead, you say you synthesize a controller. Because the way you do it is by, and we'll go into detail of these things, is by using these let's say, complex mathematical machinery that you basically just have a couple high-level knobs that you tune, and the algorithm just takes care of everything. Basically, you let the computer deal with the troubles. And another observation is, of course, when we simplify the MIMO system into a CISO one and we use the centralized controls approaches, they are easier to deal with. But typically, they are suboptimal. But they require less modeling effort. Instead, when you go with these complex mathematical machineries, you typically get optimal solutions, because we will see that these control problems are defined in an optimal way, technically speaking, in the sense the inputs are determined in such a way that you optimize a certain metric that you choose. It could be, we want to minimize the tracking error, we want to minimize the control effort, or things like this, and then you proceed in an optimization way to deal with it. But then it's very important to have a good model of the system. When your model is bad, of course, the whole thing doesn't work as well. So let's look at the centralized control a second, and I'll use a quote from our textbook that describes the problem very well, and says, the centralized control is when the control system consists of independent feedback loops, controllers, which interconnect a subset of the output measurements with a subset of the manipulated inputs. And these subsets should not be used by any other controller. So fundamentally, what we're saying is we have a plant, and let's suppose, just for simplicity, it has 2 inputs and 2 outputs. Well, we're going to control the first output only through a feedback loop that involves 1 input. So we'll feedback the first output, as we did in our classical block diagrams that you saw 1,000 times, into an independent channel from the second one, and we'll develop a controller that only takes as feedback the first reference signal, the first output, puts it together, and provides the input for the system. And so we'll do with the second one. Generally speaking, the fundamental idea is to use only 1 control signal for each regulated output. And we could write the controller in such a way where we say, so this is just a generalization in the sense that here, when we talk about 2 degrees of freedom control, I don't know if you remember from the first classes, we talked about feed-forward control and feedback, right? When we, I think it was lecture 2, when we said, there's the gang of 6, there's the gang of 4, right? So if you have a feed-forward controller, we talk about 2 degrees of freedom architectures. So in this case, we would see, well, each input, the ith input of the system, would be some controller that multiplies the reference signal minus some other controller that multiplies the output. So it's as if here we had a controller of reference system 1 and a controller of reference system 2. So this would be the first reference, this would be the second one. And of course, it's not mandatory to use the feed-forward block as well, as we've seen so far. So as we mentioned, this is a good strategy when there is a low degree of interaction between the different inputs and outputs. And another not so small detail this approach works if you have the same number of inputs and outputs, right? Because if you intended to use one input for each output, well, what if you have more inputs than outputs or more outputs than inputs? Because a multi-input, multi-output system means that the transfer, we saw that the biggest difference was fundamentally that the transfer function is no longer just a single transfer function, but it's a transfer function matrix, right? And being in a matrix, well, it could have any dimensions. It could be a square matrix, it could be a rectangular matrix. So let's start from the easy case, which is, what if it's a square matrix? What does it mean? Now, so first of all, let's assume that it's a square matrix that has full rank, right? So that we reduce it to the smallest possible square matrix that makes sense. So square matrix means that our P of S is something, belongs to each element is a complex function that has, let's say, m by m components, right? So we have the same number of inputs and the same number of outputs. So we call a system coupled if there is a structure in the P of S that is such that every input goes and affects every output. Of course, here I'm representing the 2x2 case again for simplicity, but you can imagine this, how it scales for bigger matrices. We call instead a system decoupled when fundamentally the transfer function matrix is diagonal. What does it mean? It means that each output is going to be controlled basically just by one input, okay? And so if this is the case, we are in a good shape. And if the system is decoupled, then basically what happens is that each input can affect only one output, and therefore we can see the MIMO system as if it were a union of CISO systems, and we will then use the tools for Control Systems 1 to develop a controller for each of these channels. A question again is, well, how do we choose what's the best input for each output, right? And we'll get to that later. When transfer function matrices are instead rectangular, things can become a little bit more nasty. So, of course, rectangular, we have two dimensions to go. And although I'm not really sure why these are the names, they're called tall and fat. I was up to a surprisingly old age, always thought that, I get the tall systems, right? When you have more outputs than inputs, so when L is bigger than M, the rectangular matrix is tall, so you call it a tall system, makes sense, right? But then in the other case, Claudio, did you know that when you have rectangular systems that have M bigger than L, they're called fat systems? I thought they were flat systems, and flat makes sense, but no, it's called a fat system. So tall systems are when you have L bigger than M. That means you have more outputs than inputs, okay? So what does this mean? Even if we've got the best tall system in the world, you've got less inputs than outputs. This means that there are necessarily some outputs that you won't be able to control through your inputs. So when that's the case, we'll have to ask ourselves a question. We'll have to say, well, what are the outputs that I can sacrifice, so to speak? What are the outputs that I cannot control? Because it's given the nature of the system, you don't have enough inputs, enough let's say, tools to prod the outputs to let them go where you want them to go. Therefore, the question becomes, what are the outputs that we can control most efficiently, right? So that we will keep those outputs and sacrifice the other ones. In the opposite case, instead, when the system is fat, that is, you have more inputs than outputs, when M is bigger than L, well, this means that each output is affected by a number of inputs. So the question there becomes, how do we distribute the control effort in some efficient way? Or if you want, which share of each input goes and contributes to each output control, right? So both of these problems fall under the so-called pairing problem, which is, again, the questions like which input-output pairings do we choose in order to develop our multi-input, multi-output system controller. And this question can be answered through the use of the relative gain array, which is one of the tools that is commonly used to evaluate the degree of interaction between the different channels of a MIMO system. And if you want, you can imagine this as a degree of MIMO-ness of a system. How much is a MIMO system actually a MIMO system? Well, it depends on the degree of interaction between the different channels, because if the interactions were small, well, it's just a union of CISO systems, so it's not really a MIMO one. Are there questions? I feel a ferment in the crowd. Comments? Doubts? No. OK, so what's going on here? Well, as usual, we start with some intimidating math, and then we'll break it down and see if how and if it makes sense. Let's suppose that we have a transfer function matrix, or good OP, and it's an L by M, and at the moment we do not make assumptions on the fat, tallness, or squareness of this system. And let's suppose the elements are called Pij. Well, the relative gain array, so the relative gain area of our transfer function is evaluated as this weird operation. Sometimes in literature you'll find it with the symbol, a circle with a dot inside, which is called the Schur product, or the Hadamard product. And basically it's a element by element product of two matrices. So of course they need to have the same. Let's suppose we're multiplying A by B. And of course it's an element by element multiplication, which means that the two matrices must have the same size. So let's just suppose now, for simplicity, that these are two by two matrices. Well, then if this is A11, A12, A21, A22, and B is B11, B12, B21, and B22, well, then the result is just element by element. So A11, B11, A12, B12, and so on. Okay? Now, this works directly. So the RGR relative gain area definition is, let's take the transfer function matrix and do this element by element product with what? With the inverse transpose of the same matrix. And I'm using this weird dagger symbol because if the transfer function matrix is square, then it's the inverse. You all know how to do inverses of square matrices. But what if it's not? What if it's a rectangular system? What if it's a fat or a tall system? How do you do the inverse of a rectangular system? So how many of you, please raise your hand, have any idea of how to do the inverse of a rectangular matrix? Or have you ever asked yourself, hey, can I even take the inverse of a rectangular matrix? Nobody has ever heard of the term a pseudo-inverse? I'm glad I added a safety slide on this. OK, we won't get into the details of it because you'll definitely deal with it much more in detail in some math classes and when you'll see optimization-based approaches, because they have profound meanings, but we'll talk about it in a few slides. So once we got out of the way the definition of the relative gain array, and we'll see what this means, what is the physical meaning that we give to each of the elements of this big lambda matrix? So lambda of P, let's just say that it's made of elements lambda 1, 1, 1, 1, 2, 2, 1, and 2, 2. And of course, depending on how big P is, this is going to have different dimensions. I always say 2 by 2 for simplicity. Each of these elements, remember, this is a tool to measure interaction between the channels of a MIMO system. So what really is going on is that each element is the ratio between two things. The first one, the numerator, tells us what is the gain that there is between each input and each output. If all the other loops are open. So what's the open loop gain from each input to each output? The denominator instead tells us what's the same gain from the same input to the same output if this time we close all the other loops of the MIMO system. Of course, if by closing all the loops of the MIMO system, the gain doesn't change from the open loop scenario, it means that closing all the different interactions in the MIMO system really have little effect on the single channel from uj to yi. So in that case, we would say that that channel of the system does not interact with the other ones, because whether I ignore the other channels, that is, I leave them open, or I close them, well, the gain doesn't change. So that channel is transparent, if you want, to everything else that is going on. Of course, if these numbers are, if this lambda ij is instead bigger or smaller than 1, that means that by closing the loop, things happen. Either the gain decreases or the gain increases, in which case it means that there is an interaction between the different channels. And therefore, our MIMO system is very MIMO and not has a high degree of MIMO-ness. So okay, how do we go about evaluating this? First, let's understand what a pseudo-inverse is. So again, this is really a definition more than anything else. First point, so if you ever want to invert a rectangular matrix here, it doesn't matter if it's control systems or whatever you're talking about. Well, you can't by just using the definition of inverse, because how do you even calculate the determinant of a rectangular matrix, right? It doesn't make sense. So the good news is that every matrix has a pseudo-inverse. We'll talk about the Moore-Penrose pseudo-inverse. That is, it's like the 2-norm, if you want. Like when you don't write it down, you're always assuming that it's that one. It's the most common. So if the first piece of news is that if a matrix is square, then the definition of the pseudo-inverse falls back to be that of the inverse that you know very well. Okay, so there's nothing new in the sense of if you have a square main matrix, you just do the inverse. There's nothing else to know about. If the system is instead rectangular and it has full rank, and what do we mean by full rank of a rectangular matrix? Then, if the system is tall, that is, we have a P matrix that has, again, as we said, the L that is bigger than M, that means the number of outputs are more than the number of inputs, then we call this matrix it has full rank when it has full column rank. That means the rank of the P matrix is M, that is the smallest dimension. So basically what we're saying is we find the biggest possible, let's say, square submatrix of the rectangular matrix that has full rank, intended as we know rank for square matrices. So of course, if L is bigger than M, you can't really find an L by L square included in the rectangular matrices, so it becomes obvious that the full rank of a tall matrix must be that of the smallest dimension. In that case, we talk about left pseudo-inverses. As we've seen in MIMO systems, since we're dealing with transfer functions that are matrices, matrices typically do not commute. If you multiply something by left or by the right side, it's not the same result, right? So it's intuitive that if you do inverses here, you have to talk about is it a left inverse or a right inverse, because the same concepts apply. So the left inverse, pseudo-inverse of a tall system is given by A star, which is a complicated way of saying A conjugate transpose, times A inverse, times A star. So this looks very complicated, right? Raise a hand if it looks very complicated. Yes. You'll be surprised. Now, we won't go through this in this class, or maybe we'll just do an extra class at the end of the course just to talk about these things if you really want to. But this is another of those equations that every engineer should know by heart. It's like I would never advocate for knowing anything by heart, but literally, again, if you're woken in the middle of the night, it's okay if you don't remember your name. It's not okay if you don't remember these equations, because these turns out to be super important because they are the solution to a least square problem. And so basically, I'll just do a very short thing here. Suppose that you are, let's say, measuring something, okay? And you get a bunch of data points. We know that measurements are noisy, so you get these measurements that are all over the place. Suppose that you, for some reason, because you want to find what's the best fit of these data points. How can I represent this noise through the best possible approximation, the average line that fits these points? Typically, this is solved by posing a so-called linear least square problem. So what you're doing is you're trying to find the A and B coefficients, so you can draw this line in such a way that you minimize the distance, the average distance of all these points from the line. So without getting too much into the details, this is a problem that happens all over the place. Like you'll be solving least square problems for 80% of the stuff you'll deal with in engineering. And the solution to a least square problem, x optimal, is A transpose A inverse A transpose B, okay? So somebody wakes you up in the middle of the night, what's the least square inverse solution of our problem? A transpose A inverse A transpose B, done, okay? And this comes from the pseudo-inverses. You, like, trust me, know it. Then, of course, the really good engineers remember that, no, but I have to check the dimensions of the A matrix. If it's tall or if it's fat, I have to take the left pseudo-inverse or the right pseudo-inverse, and that's already a notch up, right? But so, why is it called the left pseudo-inverse? Because if you multiply the inverse from the left side to the matrix, you get the identity matrix, which is the definition of the inverse, right? For square matrices, if you do A inverse A, you get I. But for square matrices, this is the same as A inverse. This is if square, right? In this case, of course, dimensions matter, so it's called left pseudo-inverse, because if you put the inverse on the left side, you get an identity matrix. In the opposite case, when the system is fat, instead, the definition is similar, but it's as such that the identity is obtained by multiplying the pseudo-inverse on the right side of the matrix. So anyways, this just to keep in mind that it is possible to do an inverse of a rectangular matrix. What does this actually mean? Well, that's the subject of another course. There is lots to investigate here, but we will not talk about it in this course. So, okay, we recall now, I'll just leave it up here as a memento, that the relative gain area of some P matrix is given by the P matrix itself with an element-by-element product with the P inverse transpose of itself, okay? So, these ones, and let's see how we actually evaluate these numbers. We'll do it in 2 or 3 ways so that we become confident with these approaches. First, we'll apply the definition. Like, no-brainer. We won't think, but just apply the definition. So, well, the definition, what does it tell? What does it tell us? It tells us that, well, the first thing we should do is probably calculate the inverse of this P matrix. So how do we calculate the inverse of the P matrix? Well, this is something you all know. First, we do it's the determinant of the P matrix, the inverse of the determinant of the P matrix times the adjoint P, right? So the determinant of P is clearly P11, P22 minus the cross terms, right? And this other term, the adjoint of P, we can evaluate by first, we take the transpose of the matrix, and we say P11, P12, P21, P22. Then we substitute each term with its complement. So basically, at the first component here, we just remove, we look at the first component, we remove the corresponding line and the column, and this is P22. If we do the same thing with the second one, we remove this line and this column, and we get P12. And then we can proceed and do the same thing here, and we get P21. And here we get, I finished the colors, P11. And then we add the -1 at the I plus j term to each of the elements. So for all those elements that are in a coordinate such that I plus j is an even number, this is just a 1. So basically all the odd components, you have to put a minus, okay? So at least this is how I learned how to do inverses. This means the inverse of P is equal to 1 over P11, P22 minus P21, P12 times what? Times P22 minus P12 minus P21, P11. So what is the relative gain area of P? It's the matrix itself, P11, P12, P21, P22, element by element product, with the transpose of this. So the transpose of this is, first we write the first row as if it were a column, and the second row as if it were the second column. And then we can put the scalar term wherever we want because it's a scalar. And so what do we get? So I'll just do it for 1 for the first element here. So lambda 1, 1, for example, is what? Element by element. So did I even do some mistake? All good? If you have comments, feel free to speak up. It's good if the lesson is interactive. No pun intended. But anyways, so lambda 1, 1 is P11, P22 divided, and this is something that I hate. Remember, people at home, the equal must always be on the line of the fraction. Divided by P11, P22 minus P21, P12. This doesn't look very, very meaningful, right? So let's rewrite it by just taking P11, P22, what's the English term for it? To gather out? No. Yeah, so basically we say P11, P22 times 1 minus P21, P12 over P11, P22. P11, P22, these and these guys go away, so the result is 1 over 1 minus the ratio of the cross components over the product of the main ones. So this is just applying the definition, okay? Let's not understand it. Let's just take it at face value. This is how you calculate each element. And of course, if you go and do it for the other terms, for example, this term here, you'll get similar representations. And eventually, each one of these components of the relative gain array will tell you what is the level of interaction between the jth output and the ith input. Okay? If that number is close to 1, it means that there is no effect of the MIMO system on that channel as if it were just a single input, single output one. But now let's apply a more intuitive understanding. So let's apply the intuition and say, let's actually calculate independently what is the gain of the open loop, what's the gain of the closed loop, and then we'll put them together and we'll see what happens. So how do we go about doing this? Well, now let's think about the system, right? So the system says that the Laplace domain, of course, representation of y is equal to these P11, P12, P21, and P22 times U1 of S, U2 of S, right? And this is actually Y1 of S, Y2 of S. Okay? So if we write this out, what happens is that, I'll just write it here, why not? That Y1 of S is equal P11 times U1 of S plus P12 U2 of S. And Y2 of S is equal, of course, to the other same thing. So what's the open loop gain? The open loop gain is the answer to the question, how much does Y, let's think about always for the 1, 1 component, okay? This can be changed, of course, depending on the ijth component you are evaluating, but what is the effect of the ith input? So on the first input, what's the effect of the first input on the first output when all other inputs are left constant, okay? So what we're doing is basically we're evaluating for each output what's the variation of y, in this case with yj, over the variation of ui by keeping all the other uj's constant. Very complicated to write, but what really is going on is just saying that pretend that U2 is a constant. Well, if I take the differential, the total differential of y, what's going on? Well, the variation of y1 is equal to P11, the variation of U1 of S, and this is considered constant, so it doesn't give any contribution because the variation of a constant term is nothing. So what's the gain from the open loop gain from the first input to the first output? Well, easy peasy, P11. So in this case, let's call it, I don't know, gain 1, 1 is equal to P11. And the same applies for each of the other components. So the gain of 1, 2, the open loop gain 1, 2 is going to be P12, and so on. Now, how do we calculate the closed loop gain? The closed loop gain answers the question, what is the effect of an input on the output when all the other outputs are kept constant? So there's two ways we can figure this out. let's just do them both. Why not? The first way is to say, look, just pose y2 to be equal to 0. Y2, this would be y2 of s, of course. This means that, okay, let's just write it here. This is the closed loop gains. So method A, just put y2 of s equal to 0. This implies that p21 u1 plus p22 u2 is equal to 0. This means that u2 is equal to minus p21 over p22 times u1. And you take this number and you plug it back in the y1 of s component. And we get that this is equal to p11 minus p21 over p22 times u1. You all agree? Yes, no, maybe? Yes. So again, now what's the effect of variation of the first input on the first output? Well, we keep all the other outputs constant. Well, it's p11, and it's this term here, of course. So the closed loop gain in this, let's call it the G closed loop, or these are the open loop, of 1, 1 is going to be what? This term here, which is a complicated way of saying P11, P22 minus P21 over P22. Okay, and the same thing you could do for all the other terms, which I'll spare you. So now what is the relative gain? The relative gain is the ratio of the two, right? So in this case, the lambda 1, 1 will be given by the ratio of the open loop over the closed loop 1, 1, which is, what is it? P11 over P11, P22 minus P21, all divided by P22, which means that it's P11, P22 over P11, P22 minus P21. And I have lost a term here somewhere because there should be a P12 here. So let's see. This is P21 plus. It's the nice things of doing them on the fly. Okay, so U2 has to be minus P21 over P22 U1. This is right. Ah, yes, of course. So when I plugged this back in here, so we found the U2, we had to plug it back in here. I forgot to multiply by P12, simple distraction. So this is actually, let's write it like this. Here, there has to be a P12 term. So let's rewrite it appropriately. It's y1 of s equal P11 minus P12, which is this term here, times P21 over P22 times U1. You weren't paying attention, huh? I did it on purpose to see if you were careful and nothing. Okay, so the bottom line is that here we have a P12 term as well, so you might notice the similarity. It's exactly the same as before, so of course the final result is going to be the same. Another way of doing this is going to be, well, instead of putting y2 to 0, just find the expression as a function of u2, plug it back in into the first one, and then to the total variations by supposing it's constant. It's the same result. We will not do it because I think we talked about it enough. Is it time for a break? Why don't you tell me? Why don't you just raise your hand and say, hey, it's time for a break. Why don't you stop talking? Please, sorry. Take 15 minutes break. We'll continue later. Okay, can you hear me? Yes? Okie dokie. We are running super late, so let's see what we can do. Any questions on the relative gain array? Well, if you had them, you should have come see me during the break. So let's move on. Some observations about the interpretation of these terms. Right now, we sort of convinced ourselves that there are different ways to calculate these elements of the relative gain array, and we are pretty much maybe convinced about their meaning. A few observations. First, I don't know if you've noticed, but these elements at the end of the day are calculated by some numbers divided by ratios of the elements of the original transfer function matrix. So whatever the units you use to measure those elements, it doesn't really matter because the RGA elements are dimensionless, right? So units don't matter when you calculate a relative gain array. One other nice property that this is homework if you want. Do it at home if you don't believe it, and you shouldn't. All the rows and all the columns of the RGA sum up to 1. Okay? It's normalized in this sense. So what's good is that this means that if you do it for a 2x2 system, for example, you don't really need to calculate all the elements. That's why I calculated only 1. Because if you see at the last line here, you can always, since the sum of the elements in a row and in columns always add up to 1, you can use that constraint to derive the other elements as a function of the previous ones. So for example, in a 2x2 system, you've got lambda 1, 1. Since all the rows have to sum up to 1, the next element is going to be 1 minus lambda 1, 1. So this means that if you have to calculate it for a 3x3 matrix, it's not going to take you an hour and a half because you have to calculate less terms and so on as you go bigger. Then, another observation. We are evaluating the different ratios of the gains of the different open and closed loops. But they have nothing to do with the controllers you use. Okay? This is a property of the system. It's invariant to the controller architecture that you use. There is no U's that appear in the value in the expression of the elements of the RGA. Okay, now let's a little bit of interpretation of the actual values. So what happens if your lambda is 1? Well, it means the open loop and the closed loop does not change the gain of the open loop. What does it mean? It means that all the rest of the MIMO system doesn't affect that single channel. So it's as if it was a CISO channel. So if the term is 1, the open and closed loop gains are identical. So there's no interaction on this channel. This means that this is a perfect candidate, that channel. That combination of that input and that output is a perfect candidate to choose as a pair to do the centralized control. Now, what if the element is 0 instead? If it's 0, it means either that the open loop, it's a ratio, right? So either it's the numerator equal to 0 or the denominator equal to, tending to infinity. So this means that that it's not a good choice, that input-output pair. It's definitely not the way you want to go because it means that that input has no effect on the output. So generally speaking, stepping back a second, what is an effective input to control an output? It's an input that has a big gain on the output because that means that you have a lot of control power. If you change a little bit that input, you can drive your output a lot, okay, intuitively. So when the relative gain array element of that channel is equal to 0, it's definitely a bad choice. Then, if the relative gain element is between 0 and 1 or bigger than 1, this means that there are interactions, of course. This means that by closing the loop, you're changing the evaluation of the gain. There's no hard rules here in the if to choose or not that channel for pairing. It really depends on the global considerations. If instead the element is negative, this means that there is a negative gain between the two elements, between the input and the output at that channel. This typically is a bad indication for pairing. Try not to use negative gains in a feedback control. And of course, it's not impossible, but it shouldn't. The rule is not to pick it for pairing. So, okay, I think, are there any questions about these meanings or the relative gain area in general? No. So there is a catch. I told you only the easy part of the story until now. P represents a transfer function matrix. So actually all the P11, P12 that we've been dealing with, they're not constants, right? They're a function of frequency as well. They're P11 of S, P12 of S, right? So at what frequencies does it make sense to evaluate the relative gain array? At steady state? Because, well, supposing that your system converges, then what you really want is make sure you have good performance at steady state. And then in the crossover region. Crossover region, you remember in CISO systems, we had the crossover point, right? Frequency, which was where the open loop transfer function went at 0 dBs, had unit magnitude. As we saw in the performance class, in MIMO systems, you don't just have one L function that intersecates the frequencies at some value, but we've got instead performance was defined by smallest singular values and upper singular and biggest singular values. So we got more or less these sigma big of L and sigma small of L that had to satisfy some conditions. But so we defined there were two intersections, and therefore for MIMO systems you don't really define a bandwidth or a crossover frequency, but more a region. And so generally speaking, it makes sense to evaluate the relative gain area at some important frequencies in that region, because that's where you define the tracking performances. So you get good tracking if you have good pairings in that region. So some other properties of the RGA. I will skip the derivation of these, because they're rather simple, and I think it's a useful homework. You can do it at home, and we're running late. So first, the relative gain area is invariant to scaling. Makes sense, because if you multiply the inputs and the outputs by the same quantity and you take a ratio, it doesn't really matter what you're multiplying it by, right? It's so intuitively that's the reason. And then if P for some reason is upper or lower triangular, this means an upper triangular matrix is, for example, one that has a shape like this and a 0 here. So for example, P11, P12, P21, and 0. This is upper triangular. A lower triangular matrix would have this kind of shape. So it would be P11, P21, 0, P22. So if for some reason the P is upper or lower triangular, then the RGA becomes diagonal. Why? Because if you have P element-wise products by P inverse transpose, long story short, let's say this P is upper triangular, therefore this means we have a 0 here and we have whatever you want here, and you go and multiply it element by its inverse transpose. It turns out that the inverse transpose is going to be lower triangular. We'll have something, something, something here, but a 0 up there. So when you do the multiplications element by element, this times this will be 0, this times this will be 0. Therefore, you'll get something, something, 0, 0. You can do it in detail if you want, but that's the idea. So to sum it up, relative gain area measures the degree of interaction between different inputs and outputs, and it gives us an idea on how to choose the pairings. That is, what are the most effective inputs to choose for feedback control to control specific outputs. So as we said, the ones that are most, the pairing rules are choose the channels that have the relative gain area that is as close to 1 as possible, ideally 1, because it means there is no interaction, and possibly choose pairings that do not have negative relative gain array elements at steady state, because that would generate ugly situations. So if we were to choose only, let's suppose we are in an ideal world, so everything goes perfectly and we find that our relative gain array is diagonal, right? So it means that we have terms only specific, only the ith and the jth input and output channels are connected. Then we would have this condition standing, okay? So, or actually, to say it better, let me rephrase this. The actual pairing problem means after seeing all the gains all the relative gains of the array, you reshuffle the rows and columns in order to create, as much as possible, a diagonal matrix, because it would represent only effects of on ith inputs and jth outputs, basically. And so if this condition is satisfied, in an ideal case, that would be the best case scenario, or if it's as close to the identity as possible, that would indicate something that is called the diagonal dominance. And diagonal dominance is the key element that will tell us if the centralized control is going to be effective. So if you just take this and do, oops, I always write this as an A, lambda p minus identity, this would be equal to 0 in an ideal case where the relevant relative gain area is diagonal. So we define something called the relative gain area number, which is just a way to transform this matrix in a number through the sum norm, call it as you wish, which is nothing but the sum of the absolute values of all the elements. So ideally, if it's an identity, this number will go to 0, because if lambda of p is an identity, as we said, lambda of p minus the identity is equal to 0. If we take the norms here and here, the norm of 0 is 0. So when your relative gain number is equal to 0, it means that the system is diagonally dominant. If the system is diagonally dominant, it means decentralized control is a good solution. Each channel can be controlled independently. When that does not happen, then, well, either we have to use some other approach. What other approaches can we use? Well, if the interactions are strong, that means the RGA number is different from 0. There are different strategies we can go about. One would be, say, the practical hacking way of doing it. You just detune one of the loops. So what you do is you reduce the gains on all the loops you're not interested in, so you're reducing the terms that are off diagonal in the relative gain array, and therefore you're making it more diagonally dominant. Please keep in mind that even in the best situation of the world, you'll never have an identity matrix exactly. So this is an ideal situation, but diagonal dominance is when the diagonal terms of the RGA are big compared to the off-diagonal ones. So the closest the RGA number is to 0, the better. If you have a very small RGA number, probably still something can be done. It means that there is a stronger interaction between the selected inputs and outputs with respect to all the other combinations. Another option, which is often forgotten by practitioners, is that if you set up a system where you have to control a system that has a very strong interaction, well, it's always an option to go back to the actual practical system or back to the drawing board and select the different inputs and select the different outputs. Maybe you want to put a valve in a different position. Maybe you want to consider the input some other physical quantity. So try to design your system in first place in order to make it as non-interactive as possible. Of course, that's not always possible. So when it's not possible, there are two last bullets we can shoot. The first one is try the decoupling control. What's decoupling control? Well, it's not, the system is interactive, it's not diagonal, the transfer function matrix. Let's try to make it diagonal if possible. If that fails, then we will have to use a bazooka. We'll have to use the full centralized multivariable control approaches and are leveraging all the computational power that we can. So, let's talk about some decoupling control, at least the fundamentals of it. And we'll see how the philosophy of decoupling control matches well what is called internal model control, which is one of the big families of approaches to control single input, single output systems, as well as MIMO systems. While we will not get much into the detail of IMC, because we could make a course only on this, I think it's very nice to look at because it introduces a fundamental concept that will save our life in the next classes, and we will see this. So, what is decoupling control? So the intuition, and I think we are convinced by now that what's the purpose for doing this, what's the motivation? We're trying to make an interactive MIMO system become not interactive by doing some mathematical change of coordinates, basically. So the problem would be, well, let's just add a filter. Let's add a precompensator, or maybe even a postcompensator. Why not? Such that if we go and evaluate the product of these two, the W1 of S times the actual plant, we get a diagonal plant. Is it possible? Well, so the question is, if we have a P of S that is arbitrary, it could be completely fully connected. Does it exist a W1 of S such that W1 times P is equal to some identity matrix? So it's diagonal fundamentally, weighted with some term. Well, generally speaking, no. I mean, there's no solution you can say in general that it always works, apart from, of course, the obvious approach. And what is the obvious approach? If we looked at it at, I think it was lesson 1 or lesson 2, and I asked you, how do you make a brick wall fly? I hope you'll never forget that in your life. How do you make a brick wall fly? You divide it by a brick wall, you multiply it by a jet fighter, right? So the idea there is whatever you have, if you can invert it, then you can just make it whatever you want it to be, right? Because if you have a matrix that is arbitrarily complex, but if there exists a P inverse, then if W1 could just be P inverse, so that if you do W1 times P, this becomes P inverse P, which is an identity. It's a brick wall that you're multiplying by a jet fighter. So we introduced this back in the day, what was it, weeks ago, because we said that's perfect control, right? When we were talking about feed forward, we said, hey, if you can invert the plant, then we can just make it have all the nice properties that we want, because by inverting it, you are nullifying its effect, and then you can remultiply it by whatever you want it to be, and there you go. This is the same approach this is the approach of decoupling control. It's saying, let's just find them 2 matrices or 1 matrix, depending on how you want to do it, and let's say shape the plant to be diagonal. Then if the plant is diagonal, so we found this term that allows us to do it, then the controller can be designed as a decentralized controller, which is basically a diagonal controller where each term of the diagonal is your favorite seesaw controller. The question is how to find the compensator, and the other question is how do we, where to find the compensator, because again, these transfer function matrices are a function of frequency. So ideally, of course, you would like this to happen across all possible frequencies, but often it's easier to just focus on specific frequency ranges or numbers in particular. So there are many names for decoupling control. There are many approaches. We are just scratching the surface here. But the idea is that you can always do the inverse and then make a diagonal controller, typically, or you try to do it at all frequencies, or if you have to choose, you choose the steady state frequencies, or maybe other frequencies of interest, which could be the crossover frequencies, as we've discussed before. But the fundamental takeaway of this 2 slides on decoupling control is that you can always make a plant be a strongly connected MIMO system become a weakly interconnected MIMO system by using an inverse-based design. Now, as we noted at lesson 2, there are a number of reasons for which doing an inverse typically does not work. And intuitively, if it worked, there wouldn't be as many control engineers around, right? In the sense, there would be an easy solvable problem. But the bottom line is always the same. Model uncertainty. You never know your model well. So what are you going to invert? Inversion works because of perfect cancellation. So if you know your plant exactly, then you can maybe invert it if the plant allows you to do so. But what is going to happen always is that your model is wrong. So the inversion will not perfectly cancel out your plant, and therefore this approach works only partially. Actually, sometimes it's even deleterious. And then there are other reasons. So when you do an inverse, what are you doing? So suppose that, imagine a seesaw system. So you've got your regular rational transfer function. If it's strictly proper, that means the denominator has a bigger power than the numerator. Well, if you inverted, you just got an unrealizable plant, a plant that you're making a controller that has a higher numerator than the denominator. There's no way in the world you'll manage to hook that up and make it work. It means it's a controller that will predict the future. It's anti-causal. It's not going to happen. And there are similar things like time delays. If you have a time delay in your plant and then you want to invert it, well, a time delay is based on considering effects that come from the past. If you want to compensate and cancel out that, well, you have to make a controller that's going to predict the future. Again, it's not going to happen. So while this is a very nice idea and gives us theoretical insight on the limitations of this approach, it doesn't really necessarily always work. What can work requires a little bit of a step back and talking about some important concepts. We'll see how these relate back to decoupling control when we get to the end of it. So you all remember what is the first objective of a controller, stability. And you hopefully all remember how we defined the stability for a MIMO system. There was the external stability, input-output, as usual, and then the internal stability, which was very important, because there are a bunch of other variables that evolve within the loop. And internal stability guarantees that whatever exogenous signal you go and plug in the loop, it might be a reference signal or a noise or a disturbance or some uncertainty that pops up in different ways, you want to guarantee that it's not just the output that it's bounded if you have a bounded input, but for example, your bounded reference. But you want to, for example, make sure the input to your plant is bounded as well. Because if the input to the plant explodes, it means you need infinite control power to get that output to be stable. And there is no such thing as an infinite control power. So internal stability, as we've shown before, can be achieved by ensuring that each one of the transfer functions that relate the various exogenous signals to the regulated outputs if each one of these transfer functions, which at this point we all recognize as the complementary sensitivity functions or the sensitivity functions from the output or the input, are stable. Okay? So we ask ourselves a question, since we want to here design a controller for MIMO systems, and the first objective of controller is stability, is, okay, how do we make sure that what are the conditions on C, which is the controller we want to design, such that we achieve internal stability? Is there an obvious way to say, hey, if these 4 transfer functions have to be stable, then C must have this structure, or C must have these properties? But the easy way to go about it is looking at the, okay, we can do it just here directly, looking at the relationship. No? So if you want T output to be stable, and you want to figure out what's the conditions on C such that T output is stable, well, look at what's the expression of T output. There is a C inverse, there's another C in here, and all the other ones. There is a C pre-multiplied, post-multiplies, inverse. It's not a straightforward relationship. It's a nonlinear relationship. It's difficult to say anything objective and general about, look, if you want to have these 4 transfer functions stable, C has to be equal to 43 or something like that. No, it doesn't happen, right? This is a quote, by the way. If you didn't get it, you should read The Hitchhiker Guide to the Galaxy. But anyway. So there's something beautiful that goes on. So 43 is the answer to all the mysteries of the universe. So there's something called the Q parametrization. It's or otherwise known as the Euler parametrization. Are we all good? You can check it out later, the 43 thing, but it's important. 42, yeah. Sorry, 42? Oh. Oops, please erase that part from the camera. Okay, anyways, yeah, thank you for the correction. We introduced this concept, like, follow me on this. I know it's the last 10 minutes, we're a little bit tired, but this is like a very nice and powerful result, so I would like you to stay strong for the last 10 minutes. Suppose we define a Q function as C times I plus identity plus PC inverse, okay? It's basically C times the output sensitivity function. Then we can see a few properties. And we see, look, if you just take I plus PC inverse, this is equal to I minus PQ. In fact, if we just look at I minus PQ and we represent the I as I plus PC times I plus PC inverse minus P times Q, which is C I plus PC inverse, well, this can be rewritten by gathering this inverse part on the right as I plus PC minus PC times I plus PC inverse. These and these go away, and so we convince ourselves this is equal to the other part, right? So if we do a similar approach, we can just a similar passage, we can demonstrate the second one, then the third one is obvious because it's just the first one multiplied by P. we can see that we can relate some of these nasty inverse terms of the sensitivity function, of the relationship between the controller and the sensitivity function, as linear relationships with Q, or at least there isn't inverses going on. So if we write the important sensitivity functions which we want our system to be, which we need to be stable for our system to be internally stable, we can easily make them show up to be very easily related to the different Qs, okay? And the derivation of these four properties is pretty much just applying the definition and one or more of the three equations below. So now look, the output sensitivity function is no longer related to the inverse of C and some other weird relationships, but it's simply Q multiplied by P. Okay, if you look at the other four transfer functions, either just Q or Q multiplied by P, or just very easy relationships. So what does this tell us? This tells us that if, and this is a big if, the plant P is already stable, then the closed loop of a MIMO system of whatever you want complexity and interaction is going to be internally stable, guaranteed, if Q is stable. So why is this relevant? Well, because to guarantee internal stability, let's say you have a system, you design a controller. If you want to check now if the MIMO system is internally stable, well, you have to evaluate the stability of these four functions, which means you have to go and find what's the characteristic polynomial of I plus PC and go and see if that's it's stable or not for the different things. Now, all you have to focus about is the denominator of Q. Done. Plus, you can now have a very easy way to tune the different performance and robustness of your system, because all you need to focus about is Q. But then one could ask, of course, if I find Q, is it the same thing as finding C or not? I mean, we know that there's one controller for the system, and this Q thing seems like coming out of nowhere. So does it still hold, right? Well, the really powerful result is that if you take one of these properties here, which is this one, actually, no, sorry, the definition of Q, you can just easily invert it and determine a relationship of C as a function of Q. There's a one-to-one relationship. Given a Q, you get for free a C. Given a C, you get for free a Q. There's no indetermination. How do you get this? This is just well, we multiply both sides of the equation by the inverse term, so we get C is equal to Q times I plus PC inverse, and not, sorry, PC normal, because we multiplied by the normal part, not the inverse, and this is therefore Q plus QPC, and this means we can bring the term on the other side, take the inverse, and we get this other equation, okay? So what is this? This is the parameterization of all possible internally stabilizing controllers given a stable P-plant. All possible controllers that can ever come to your mind that internally stabilize a MIMO system, if you have a stable P-plant, are represented by this equation. It's very powerful, very powerful. What if P is unstable? Well, if P is unstable, you can get to a similar equation. You have to do some intermediate passages, but the idea is that you superimpose another preliminary controller that stabilizes the plant, and then you do this. Again, we use the usual approach. If you have a problem that you don't know how to solve, just make so it becomes a problem you know how to solve and use the tools you have. We're not going to get into this, but if you see the references, it's easy. Now, in 3 minutes, there's no way in the world we're going to do internal model control. So let me focus just on a few high-level ideas. This representation of a controller that represents all the possible controllers in the world that stabilize your plant happens if we were to open it up, untangle it, and write it down as a block diagram to be the controller, so this big red box, if we write our control system like this. So what is the difference between this and what we are used to looking at? The difference is that instead of having just our reference coming in and comparing it with the system output, or at least the measure of the outputs of the system, and getting our tracking error, and then we feed in a controller that goes into the plant. Now I'm forgetting all the noises and stuff, but that's not relevant at this point. So instead of feeding back the output, what we're feeding back here is the difference between the output and the output of a model of the plant that we have. You can make up this model. I mean, of course, the closer it is to the real system, the better. But the idea is that now our controller encapsulates, includes inside its own definition, an idea of what it's trying to control, a model of the plant. This is called the internal model principle, which states explicitly that accurate control can be achieved only if the control system encapsulates some representation of the controlled process. Now, if this... so the interesting part is that what goes to drive the controller now is this signal here, which is y minus y naught. So y is the actual measurements, as usual, while y naught is the output of a model. So the model is what you know. The plant, you do not know. So we can call the output of the model a prediction, if you want, because if we know the mathematical behavior of a system, and we can write it down with differential equations, for example, well, then we know everything, right? We can use our math knowledge to see what's going to happen to the output in the future, for example. Once I give you initial conditions and differential equations, you can pretty much do whatever you want with them, right? So imagine this as a prediction of what's going to happen. Well, imagine the measured output by a noisy version of what is actually happening. So now in the system, we're not just measuring feedback, we're not taking decisions based only on the measurement, a noisy measurement of what's happening, but we take decisions based on the difference between our prediction, our belief of what should happen, and the actual measurements. This is an incredibly powerful idea that will drive all the next 2 classes. We will basically use this to introduce incredibly powerful concepts like state observers and state feedback and things that are going to change our lives as controllers. So, unfortunately, I do not have the time to continue this, but we will continue next class from here. Are there any questions? No? Well, yeah.